When Albert Einstein set the speed limit of the universe at the dawn of a new century, he proved that the space around us and the time that we perceive are two sides of the same thing.
Earlier this year, after a span of 15 years of intensive search, scientists have at last detected the faint background hum of low-frequency gravitational waves that permeate our universe. This marks the start of the demanding task of identifying the origins of these ripples in the fabric of space-time. So, what's causing these mysterious ripples in space? Let's explore the recent findings and uncover the secret behind these puzzling vibrations. Presently, the key candidates under investigation are pairs of supermassive black holes boasting masses in the millions or even billions of times that of our Sun. Nonetheless, this doesn't eliminate the possibility of a few less conventional suspects. These outliers could potentially serve as clues guiding us toward novel insights in the realm of physics. The significant breakthrough was achieved by researchers belonging to the North American Nanohertz Observatory for Gravitational Waves, NanoGrav collaboration. They meticulously studied 68 rapidly rotating neutron stars, often referred to as pulsars. These pulsars emit radiation in sweeping patterns, regularly intersecting Earth. This unique behavior transforms the pulsars into extraordinarily precise cosmic timekeepers, referred to as pulsar timing arrays. As gravitational waves travel across the universe, they cause space and time, which together form what we call space-time, to stretch and squeeze. Scientists can combine data about this effect with information from pulsar timing arrays to eventually create a detectable signal, or what we call a spectra, that researchers can study. It's not the first time scientists have noticed gravitational waves, though. They first detected these waves using the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015. However, those waves were of a different type, with higher frequencies and shorter wavelengths. They came from sources like small black holes in space. What makes the gravitational waves spotted by NanoGrav different is their wavelength. They have much longer wavelengths. Scott Ransom, an astronomer from the National Radio Astronomy Observatory, NRAO, who was previously in charge of NanoGrav, explained, "If you think about it in terms of the electromagnetic spectrum, NanoGrav is like radio astronomy, and LIGO is like X-ray astronomy. This means there's a huge difference in the frequency and size of these waves between NanoGrav and LIGO. Let's put this in simpler terms. The gravitational waves that LIGO found have wavelengths of thousands of miles and frequencies of milliseconds to seconds. But the new gravitational waves from NanoGrav are much longer, stretching over trillions of miles. This is like the distance between our Sun and another star called Proxima Centauri, which is about 20 light-years away. Also, the NanoGrav waves have much longer frequencies. They happen over years instead of just seconds. What this practically means is that scientists need to collect data for more than 15 years to be sure they've found a low-frequency gravitational wave. It takes a while, but the wait is worth it. That's because these findings could reveal new things about our universe. Pulsar timing array experiments are definitely long-term experiments that you have to be very patient with because our signal slowly grows with time," Ransom said. The detection of low-frequency gravitational waves means they're from very different sources to the LIGO and Virgo sources, which are stellar mass black holes and neutron star mergers. So, who is the main suspect here? None other than supermassive black hole binaries. Ransom is part of a team of researchers who have an astonishing idea about where these low-frequency gravitational waves, like the ones found by NanoGrav, might be coming from. They suggest that these waves could be coming from something truly incredible. Hundreds of thousands of supermassive black hole pairs that, over the incredibly long span of 13.8 billion years, got close enough to merge. According to Ransom, these gravitational waves happen because the supermassive black holes are circling each other for hundreds of thousands of years. But, at some point, the waves they create stop, and that's when something amazing happens. The waves take away some of the spinning power from the black holes, and this causes them to finally crash into each other. That's when they were pumping out these big, massive gravitational waves and losing their energy so that eventually they're going to collide, Ransom said. But we didn't know how many of these supermassive black hole binaries there were. and we didn't know how massive they were. And all of that determines when you're going to finally detect gravitational waves. The team's discovery lines up with what scientists have been expecting to find when it comes to supermassive black hole pairs. For many decades, theorists have hypothesized that supermassive black hole binaries should produce a signal with characteristics just like what nanograv and other pulsar timing arrays are seeing, said Luke Zoltan Kelly, a theoretical astrophysicist from Northwestern University and part of nanograv. For most of the community, supermassive black hole binaries are a natural best guess for what's producing the gravitational wave background. However, this doesn't mean the case is completely solved yet. Scientists need more concrete evidence before they can confidently confirm the presence of supermassive black hole pairs in our universe. The challenge with binaries is that no example of a supermassive black hole binary has been fully confirmed before, so we don't actually know for certain that these incredible objects exist, Zoltan Kelly said. That being said, it would be an even bigger puzzle if they don't exist, because we know that galaxies contain supermassive black holes, and we know that galaxies merge as a normal part of their evolution. Adding to this cosmic enigma is the fact that other research groups are investigating different possibilities for the sources of low-frequency gravitational waves, introducing more unique suspects into the equation. Zoltan Kelly pointed out something interesting. Besides supermassive black hole pairs, there are other ideas in the world of cosmology and particle physics that could also make the same kind of gravitational waves that nanograv found, if the right conditions are met. For example, there are ideas like axion or fuzzy dark matter, cosmic strings, inflationary phase transitions, and more, explained the astrophysicist from Northwestern University. What's really exciting about these possibilities is that each of these models is an attempt to explain some of the biggest current mysteries of our universe. Some of these mysteries are about dark matter, which is a type of matter that makes up around 85% of everything in the universe, but can't be seen because it doesn't interact with light. There's also the puzzle of why the universe started expanding faster again after the Big Bang. In my mind, it's a win-win. If the background is cosmological, it will completely transform our understanding of the universe and of fundamental physics, potentially one of the biggest discoveries in the history of science, Zoltan Kelly continued. If instead, the background is from boring old supermassive black hole binaries, then we get to explore how the most massive objects in the universe are able to form pairs and spiral together while emitting more energy than most entire galaxies do over their lifetimes. The good news is, there's a way for scientists to figure out where these gravitational waves are coming from, especially if the waves are stronger and brighter from one direction in the sky. This could help them confirm the source of the waves. The next important step is to confirm where exactly these gravitational waves are coming from, Zoltan Kelly explained. We believe we can do this by studying the differences in their strengths across different parts of the sky. If supermassive black hole pairs are causing the waves, we should notice differences in brightness from various parts of the sky. But if the source is something cosmic, like cosmic strings or phase transitions, then the gravitational waves should look almost the same all across the sky. Kelly, the astrophysicist from Northwestern, also mentioned that the team is excited about going a step further in this research. They're aiming to possibly find the individual black holes that combine to create these gravitational waves in the first place. This would be an amazing opportunity to spot these sources using regular telescopes that detect light, added Zoltan Kelly. We're working hard to figure out what kinds of signs of binary black holes we should look for in active galactic nuclei, AGN, or quasars, so we can start searching for them. Even before the nanograv researchers can confirm exactly where these low-frequency gravitational waves are coming from, just detecting two types of these space-time ripples is extraordinary. It's especially impressive when we remember that Albert Einstein, the person who first predicted gravitational waves in his 1915 theory of general relativity, also predicted that these space-time ripples would be too faint for us to ever detect. I think it's amazing, for one thing, that the state of astronomical technology and research has advanced so much that within a decade, we opened up two completely independent windows of the gravitational wave universe, Ransom concluded. So, what are your thoughts about this? Let us know in the comments. We would love to hear them. With that said, thank you for watching. Don't forget to hit that subscribe button and stay tuned for more.